Welcome to the Astrophysics Podcast. Every single human on this planet is susceptible to a thing called confirmation bias. Every one of us, and we always have as long as humans have been walking the earth. It's a sneaky way that we trick ourselves into not critically thinking about things as much as we should. And before you think to yourself, yeah, a lot of people I know are like that, I'm talking about all humans, including you and me. And actually, it's even worse for artificial intelligence. Arguably, AI is a sort of personification of confirmation bias, so don't think it will get any better when the robots take over. In science, we actively try to work against confirmation bias, but we are just as susceptible as anyone else. A great example comes from back in the 1910s and a famous physicist named Robert Millikan and his student Harvey Fletcher. Millikan was trying to measure the electric charge of a single electron in an extremely delicate experiment involving drops of oil suspended in an electric field. Millikan did measure the electron charge pretty precisely. His error bars were about plus or minus 1%. But the true value of the electric charge that we know today is a little bit larger than what he had measured at the time. Over the next 20 to 30 years, as scientists devised different experiments to check his work, a very unusual thing happened. If you look at their papers, they all seem to measure values larger than Millikan's value, but then they explain it away by some issues in their experiment and perform some unjustified math to explain how the correct value should actually be closer to Millikan's measurement. Millikan was a towering figure in the physics community by this point, and if your results disagreed with his, people felt like they must have done something wrong and readjusted their math or threw out some data points and accepted others until they agreed with previous results. As you may have figured out by now, all these other scientists weren't wrong in their experiment. It was Millikan's result that was incorrect, or to be more precise, his quoted error bars were too small. Ultimately, the community at large was suffering from confirmation bias. Our results needed to first agree with previously established results in order to be believable. This was a particularly egregious example, but in general, confirmation bias is all around us. Everyone builds their own particular worldview, and we tend to listen to data that agrees with that worldview and dismiss data that disagree with that view. And absolutely everybody does it. One way this can happen in astrophysics is you'll take some observation of the universe and you decide it looks like something you've already seen before, so it's not worth devoting the resources to keep looking at it. This is a common issue in transient science. You can't follow up on every single supernova, every single gamma ray burst, or fast radio burst. So we have to pick ones that we think are interesting and move on when we think they've finished being interesting. But that means if your object later does something that you didn't expect, you'll never know it because you've stopped looking at it. So that's confirmation bias in astrophysics. But sometimes we can be brave and follow up on things when we're not sure whether or not we'll see something new. And that brings me to my guest today. Dr. Yvette Cendes is a radio astronomer and professor of physics and astronomy at the University of Oregon. And she's managed to make some pretty powerful discoveries by following up on explosive events long after everyone else stopped looking at them. As a result, we're learning all kinds of new things about tidal disruption events, or what happens when a star gets shredded up and eaten by a black hole. I'm Paul Duffel, and this is the Astrophysics Podcast. And that, because the whole point is it's a dialogue, so
Yes.
we can clarify it that way. So
Okay.
that's totally fine. Whatever, this isn't your first rodeo to
No,
public.
you're not my first podcast, so I'll probably be okay.
Okay, good. So you're not worried. Yeah, okay, so that's fine. I had this sort of list of things to prepare. Yeah, and you're welcome to do your, if you want to do your catchphrase, you want to say.
If it comes up at some point, we can do it.
I wish I had a catchphrase. I just have "Welcome to the Astrophysics Podcast," but that's
Okay.
that's all I can do. But maybe one day. Okay, are you ready?
Sure.
Okay. All right. So welcome to the Astrophysics Podcast. My guest today is Dr. Yvette Cendes, Professor of Physics and Astronomy at the University of Oregon. Dr. Cendes, thank you for joining me on my podcast.
Thanks for having me.
Do you
Yeah.
do you remember when we first met?
We first met in October 2019. I was started at.
You remember the month?
Well, I know the month I started at the CFA, so Harvard.
Okay.
And yes, there were alcohol pods involved. I don't know if you can put that on your podcast, but
that phrase is allowed to be put on my podcast.
Okay. Yeah.
Well, basically anything at the Harvard Center for Astrophysics, alcohol will be involved. So I don't remember that specifically, but I'm sure there was.
Yes, there was an experiment on how to make Tide Pods that had alcohol in them.
Oh, right. Oh, man.
And I was like, good Lord, where did I end up?
Okay, so large portions of this episode might need to be edited. All right, so that's fine. That's okay. But anyway, good. All right, so let's get started by just talking about you and how you got into science. So let's start by asking, where did you grow up, or where were you born at first?
I was born and grew up in the same place, which is Pittsburgh, Pennsylvania.
Okay.
So, yeah.
And what was Pittsburgh like?
Pittsburgh, as I've known it, has never had the steel industry. That was before my time. But we also didn't have Google yet. So it was the decline. It was the in-between of being the trendy hipster town. And so growing up in Pittsburgh, the way I always describe it is next to my school, when I was in middle school, there was a Nabisco factory, which was great because it smelled like cookies every once in a while. They made the vanilla wafers. Then it shut down and there was nothing for the rest of high school. And now that's the headquarters of Google. So I feel that is the Pittsburgh story.
Right. Yeah. That's very good. That's a nice summary of that. And so do you have like a memory back then in Pittsburgh of like the first time you got interested in science?
So I guess there's kind of two stories to that. Okay. The first is when I was 10 years old in 1996, the comet Hyakutake came, and I remember my dad taking us out to the country to see it, but you could actually see it from our backyard. It was the naked eye comet. I remember there was a joke at the time where my dad was like, it has a 8,000 year period, thousands of years period around the sun. Right. So he joked to us kids, think about me the next time you see it. And I think that was the first time as a kid that you realize there's things that were going to last far beyond our human timescales.
Yes.
And then the second was I really decided to become an astronomer when I was 13 years old. I had a very long school bus ride home. So I frantically needed to find a book to read on the school bus to go home because I always read on the way home and didn't have anything. Okay. And picked up a book on astronomy in the library for whatever reason. And by the time I finished that book, I was like, this is the coolest thing ever. I wanted to be an astronomer and never really changed.
So it was just a book that was randomly sitting there and you grabbed? Or?
I wanted to look up an astronomy book for a reason I can't recall now. Okay. And that book was called From the Big Bang to Planet X by Terence Dickinson. Okay. And it just kind of had like little bits about everything. And I've always liked stories, and the story of the universe is the biggest one we have.
That's funny. So now this is actually the idea that you pick up a book about astronomy and then that like suddenly your mind gets really opened up. Like that is multiple people have reported a story like that.
Yes.
In fact, my last guest, Maxim Ludikov, found a book on the ground while he was on a kayaking trip with his parents.
That's an even crazier story. Yes.
It was just a book on astronomy. But anyway, I thought it's funny that that's such a common experience. I don't know why that would be, but I mean, part of it, I mean, it did have nice pictures in it that like, or was it just?
Not even, it was more the story. So like, I'm a bit of a storyteller. I think like being a scientist is also being a storyteller in some senses. Yeah. And I was just really in love with that side of it.
Yeah, well, that's cool. So do you now, were your parents' influences on getting into science?
Yeah, for sure. So my dad's an electrical engineer, well, retired now. But yeah, so he was very excited about, I think, his daughter being interested in astronomy. Definitely bought me a telescope in high school and things like that. And we've had many, many science discussions over the years. My mom was a middle school math teacher. Wasn't by the time like she was raising us instead. But yeah, so it was a very pro-science household, I think it's fair to say.
So they were very happy about that, getting interested in science and wherever you wanted to take it. So were they mostly supportive of just wherever you wanted to take it?
Pretty much. I don't recall anything like once I was like, I want to be an astronomer. My parents were never like, oh, are you sure you don't want to do this or that? Instead, it was always, I think. Right. I was also, to be fair, probably pretty solidly obsessed about astronomy, so they probably realized like, that wasn't going to go very far. Yeah.
Okay. And so that was you growing up in Pittsburgh, and then so where did you go to college?
I went to college at Case Western Reserve University, where I got my, which is in Cleveland, Ohio.
That's in Cleveland, okay.
Yes, and I got my bachelor's in physics there, and I also got a master's in physics there.
Okay.
Actually.
And were you like thinking astronomy then already?
I was, and it was actually interesting because Case has the smallest astronomy department in the country. At the time, it was 3 professors only.
Okay.
And that's for historical reasons, basically, that there's astronomy is separate there. And astronomy and physics were basically just like, do you want to take upper level astronomy classes? And like they did more like galactic halo type research. Mm-hmm. Or there was a huge particle astrophysics group in the physics department, and you did a lot of like upper level lab classes.
Okay.
So I actually ended up with a physics degree, which surprised me because I found that just more interesting, high energy astrophysics type things more interesting, and that was in physics.
I see.
So that's kind of how that happened.
Okay, so your bachelor's degree is in physics.
Yes.
And then,
but this is why I tell people it really doesn't matter.
It really doesn't matter.
No.
Right, that's right. And like, I mean, that's my bachelor's and PhD are in physics. Mm-hmm. And so, yeah, I mean, it's, they're very closely aligned. Mm-hmm. So you end up, at what point do you feel like you learn how to be a scientist?
That's an interesting question. I'd say during my PhD. Okay. Probably like, because I mean, I did undergrad research and this and that, but that's kind of like small projects that you don't see all the, like, I'm not saying you don't see them all the way through all the time, but it's kind of like, they're a bit more contained, and you're not in charge of driving the project, I think, when you're still a student, because you're kind of just doing something that's a bit more set up, or at least that was my experience.
Right.
I'm not saying like I didn't enjoy those experiences and learn from them.
Yeah, of course.
But I think being an actual scientist and having like the expertise knowledge of a field and like the systematic way of thinking about it really kind of, maybe I'm taking a more overarching view now, but I feel like that was really grad school for me.
So then where did you go to grad school?
I went to grad school. My PhD is from Leiden University. In the Netherlands.
So how did you apply there starting from the US? Or
yeah, so I have as I said, I did a master's, and that was basically, I was on PhD track, but I wasn't really interested in the science for PhD at Case. Mm-hmm. And I actually did a semester abroad in undergrad, and I really, really wanted to do more, living abroad more. Mm-hmm. And I did a bit of traveling and this and that. I went to New Zealand for a semester. That was my thing. And so I wanted to basically live abroad. So for PhD in Europe, you need to have a master's degree.
Right.
So it was like, I can do this. So I applied Germany, the UK, the Netherlands, and the Netherlands worked out.
Okay.
And I lived there 5 years.
Okay.
So, yeah.
Oh, that's cool. And so you were at Leiden for 5 years.
It was a little more complicated. Okay. I was in Amsterdam for a few years first, and then I was in Toronto for a few years, and then I ended up getting my degree at Leiden University. Yeah.
Well, that's pretty nice. That's cool. And so then, so that was the part where you felt like you were. So what were you working on there, where you felt like you were suddenly now you're actually driving the research, or you're?
That's kind of interesting. I think it really was. Like, I did a project, it was Supernova 1987A, and it was kind of the evolution of so Supernova 1987A, for those who are not familiar with astronomy, is a very famous object because it's the first supernova, or the closest supernova that happened to us since the invention of the telescope.
Right.
And we've been studying it ever since, because it happened in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, about 120,000 light years.
Oh, maybe, you're looking at me like...
Anyway, so astronomically close, not like next to us close, but you could see it with the naked eye for like a month when it happened. Yeah. And anyway, so you could still study the radio emission from it. It's actually brighter now in radio than it was when it first happened, which is kind of a fun thing. But so kind of learning the analysis of that and putting that all together. And I think that was the first time that I was really kind of just... you're familiar with this feeling. You're staring at the page and you're putting the pieces together, and like, what is the story here that I am going to have that's enough to like get off? Yeah.
So okay, and so, sorry, just to clarify, so you were looking at this, of course, 1987A went off in 1987, so you were looking at, you were looking at it much later.
Yes, so this is data from the 2010s.
Right, and so you were seeing how it's...
so basically what you see in radio is there's, it's called circumstellar material, so material that was poofed out by the star before it died, and the shockwave from the supernova, like this material was emitted tens of thousands of years before the supernova happened. But the shockwave goes outward and it starts interacting with that, and that really lights up in the radio.
Okay.
And what my data was studying was, so the shockwave went into this ring, and you could actually study the expansion of it. It slowed down, and then my data set showed when the shockwave left the inner region of that ring where it had slowed down, it actually reaccelerated, which is classic angular momentum, right? Because there was a material, so it slowed down, and then once there was no longer material, of course it wasn't as fast as when it started, but it was faster.
Right.
And that was kind of putting that all together, and I was like, wow, I feel like I've really made a discovery. I guess that's really what it is for me.
Okay, so in other words, you got to look at your data and then not just say like these are the answers we got.
Yeah, this isn't just like these are the parameters, or this is like I did my first stuff in my PhD was very like technical stuff and bringing that online, which is really more an engineering thing I think than feeling like a scientist in some senses.
Right.
So that's why it's like remembering that was my first project where I was like, oh, I'm saying something new about the universe that nobody else knows,
Right.
Which I think is when you want to be an astronomer as a kid, that's kind of what you're going for.
That's what you're hoping for, is you're going to like be the first one to look at this and be able to say something new about...
tell a part of the story.
Yeah.
Yes.
That's very cool. So now you're an astrophysicist. What do you like the most about your job?
Oh, that's a good question. Yeah, I like a lot about my job. So I started my current job in September. So there's a lot about it that's very new. I think what's cool about it is, you might be familiar with this feeling, but people always ask me like, what's the most interesting thing right now in astronomy? I'm always like, I honestly think it's whatever I'm studying at the time.
That's right.
Because I know that problem the best.
Yeah,
so I know everything. Right. So knowing this problem and driving it forward, and now I have students, which is an interesting experience, my first PhD students and undergrads, and like getting them familiar with everything and bringing them forward. And it's very satisfying to see that they'll now like show up with their own, like, look at this light curve, and you're like, wow, cool. Or sometimes they do things even better than you would have yourself, and you're like, wow, this is very efficient, cool.
I love that too. I'm working with students is exactly the thing you just said is like kind of the best thing is because the students think differently than you, and at first, if you're like being very rigid, you're like, no, you're not doing this the way I would. But then if you're sometimes they'll like it will be better that they're not doing things the way you would.
I mean, I think so. There's a few things I've realized, like becoming faculty versus the stages before. The first is it's really a management job, and your first real switch to management. But I think the second thing is by now I also just have enough science that I could no longer do it all myself.
Yeah.
And that's kind of the natural point to then branch off, and then you start a group to do science devoted to what you're interested in.
I have felt the same way when I first started. Like I had I started to build these lists of things to get around to, and I just never got to any of them. And it's really nice to be able to be like, maybe you could work on this, and then like I don't have to have that, we're in the back of my head on my list of like I should be doing this.
Yes.
So that's very nice, and it's also it's great when they're good at it, and so that's very cool. So mostly, so you touched on advising students, and that's the main that's the thing that jumps out at you.
Yeah, that's been the main one. I haven't actually started teaching yet. I'm still on teaching release. Well, we do quarter system in Oregon, which I don't know if you're familiar with, but it's very strange in some senses because like. I got teaching release for 2 quarters, which means our spring quarter is March 31st to mid-June. Yeah. So it's going to be all of astrophysics in 10 weeks. So I think that's going to be a bit of a baptism by fire for the teaching side.
It's funny. Yeah. When I was an undergrad, we at the University of Washington, we had quarters. Yeah. And I liked it a bit because you got to change things up. You weren't stuck in the one class for this long. But for the teachers... It's basically one more exam to give, one more this and that. It's you have the courses aren't redesigned based on the quarter system, so you're cramming. We have some weird ones that are just like this didn't quite fit, so we have to do like a third quarter first year freshman class that does like the grab bag of
stuff.
Right.
And yeah.
Yeah, but I'm realizing after the fact that all these courses are designed for semester length, and so like textbooks are written with that intention and that sort of thing.
Indeed.
So you end up being like, okay, which parts of this do I teach?
I mean, I think the other thing though, like to go back to your original question, like I think the thing that we're very lucky about in our jobs is that we're all passionate about a similar thing, and we get to hang out with other people all day who are passionate about what we're passionate about. I think that's really kind of something where I'm thinking like, oh, I'm excited to go to work. Why is it? It's like, well, because I get to go and see people and we get to have conversations about exciting things to us. I'm sure other people were like, oh my God, kill me now if you had to hang out in an astronomy department all day. But
I love that too. I think that's the best. Yeah. And it's good. It's fun because I don't think anyone else has answered that yet, but I didn't even think about it, but how much I enjoy that part of my day. Because if I didn't like that part, I could work at home every day. Nobody would stop me. But I obviously like showing up and seeing what's going on. Yeah. That's right. Is there anything you don't like about your job?
I mean, I think it's very important to emphasize to younger people in particular who are looking for things like every job has something in it that you don't particularly enjoy.
Right.
Like there's no job. The question is how much you like the rest of it to make up for the stuff you don't like. So like, I don't know anybody who likes paper corrections, for example. So like, when you get your referee report and you get to go back through and say, dear referee, thank you for your kind comments and your and then just nobody likes that. Like, let's just be full up, So I think there's that.
Yeah, that's right.
Learning some of the admin stuff, as I said, now that it's a management job, can be annoying. A bit annoying.
I combat that by not learning any of it.
Yeah, that is the professor trick. You realize if it's really important, they will eventually tell you to actually do it. So that's definitely those are definitely the usual answers, but I figure I might have, since I asked what you like. No, that's fair. I think it's important to say what.
It's funny that so I asked that questions because I think people don't reflect on that enough. And some people, like, for example, I know a lot of professors that don't like teaching, and I think to myself, what? Yeah,
that's a bit. I feel bad for the students then.
Right. So I always find that funny, and it's good to kind of reflect on that. Like, yes, there's always going to be things you don't like about your job, but like think about,
the things you like instead.
What are the things you like, and
it's interesting. So one of the things that I also like, if we're thinking, which is specific to my specific field, is scheduling VLA observations. So the Very Large Array in New Mexico, the way it works is they have a queue. So you set up and you don't have to go yourself to observe. There's an observer there who does it.
Right.
So you have to submit your observations, and like it's a very particular website. It's written in Java, which already tells you this is a mistake. And it hasn't been updated in many, many years. And it's kind of one of those where it's like they give you all the options in case somebody might need one of them, and most people just don't need all those options. You know what I mean? And anyway, as a result, scheduling it is just terrible. But the nice thing about students is it's like, well, one of the first things you can do is offload the schedule.
You can be like, oh, this is something you'll need to learn how to do.
Yeah, and then like they're actually very excited about it because it's like, oh my God, I get to do VLA observations, and you're like, yeah, cool.
And they'll probably pay more attention when they're
yes, indeed. So I guess that's something like I've outsourced one of the more unpleasant things about my job. So.
It's funny how that's a great example of things like astronomy is one of the most to me rapidly changing fields, because we're adjacent to physics, which does have big changes but is much slower. Like we still teach from the same textbooks we did maybe a century ago in physics, but in astronomy the whole field changes over a generation, like what we know to be true. And so it's funny that we're just as bad at change in terms of using antiquated systems.
I mean, I think in the sense of the VLA, it's a question of how much money are you going to spend for the full upgrade.
I guess so. I guess so. But anyway, but there are lots of examples of that in astronomy where people have conventions that they just stick with.
Like people who still use Fortran. Yeah.
Hey, don't knock Fortran.
Okay.
So, what would you say then? I guess what would you're an astrophysicist now, and what would you say would the biggest challenge getting to where you are currently?
So the biggest challenge was actually also my PhD.
Okay.
And we'll see how much I'm going to let you keep in this podcast. But the long and short of it was I started my PhD in the Netherlands, and I had a very tough time with my first supervisor. And I think in hindsight, hindsight being 2020, he didn't really take me very seriously as a scientist.
I see.
And also I was hired to work on a project that didn't work.
Oh.
So as I was saying, it was a low frequency array.
Yeah.
There's a lot of technical challenges with the project I was involved with, this and that. And so basically 5 years or so into my PhD, I could no longer finish with that supervisor.
Wow.
And I had to switch supervisors and universities. So it was actually at the
I see.
Yes.
And so that was why the jumping around.
Yes, happened during my PhD.
I see.
And that was very difficult. The easiest thing for many, many people would have been if I stopped. Let's put it that way. But as I said, I just really never thought that I wanted to do anything else. And also I did not feel I was being treated fairly in the situation.
Right.
Because of course, the problem with if you're a PhD student and the project isn't going well, the problem is you. That is the conclusion. It's much easier for everyone. And to be no, I'm actually not getting a fair shake here.
Right.
And just need a good opportunity to go forward and prove myself. That's pretty tough to get. Yeah.
That's what you just described is the sort of thing that can happen to a lot of students, because it's one of the things that when you're a grad student, you're just starting out, you don't know what is a reasonable project to be working on, what is a reasonable circumstance for your PhD, and what is a reasonable advisor expectation,
Yes.
And so you'll get your PhD advisor, and if they could be really horrible, give you really bad advice, and you have no idea because they're your advisor.
Yeah, and also if you're not being managed and you try to manage yourself, well, you've never learned how to do that.
Right,
so that's also part of it. Yeah.
Right, and so you don't have that outside, now I can look at those situations and see when a student isn't getting a fair shake, but when you're the student,
when you're in it, it's very hard.
Yeah.
There's a lot of things I think in all stages of our career we look back on and you're like, that wasn't so normal or something like that. And now you know it, but hindsight is 2020.
Right. And you're right. A lot of students, they just say, well, I guess this isn't for me, and then they just drop out. So I'm glad that you stuck with it.
Yeah, well, me too. It was definitely a tough period, but there's definitely been multiple times since where I was just it was worth fighting through.
Right.
So if anybody out there is having a tough time right now, I can assure you that if you come out to the other side, I found it very rewarding.
Yeah.
So.
And the other good news is now you are able to, you can identify situations like that potentially.
Yes,
and be able to give.
I get a lot of career advice questions through Reddit these days.
Oh, really?
A couple students a month. I mean, not situations like that. Those are thankfully much more rare, but I do give out a lot of career advice. And as I said, I now have students, which is a little terrifying when I feel
Right.
It's a lot of what not to do advice. So I don't know if that's,
Good. I know I think about that a lot too, of making sure I'm not giving students dead end things and but that's it. You'll be more cognizant of that. So hopefully.
I think at the end of the day, there's so many interesting things to work on that. It's the idea that I was sitting around for 6 months and had nothing to do, for example, in my fourth year. In hindsight, I'm why? That makes absolutely no sense anyway, unless somebody wasn't paying attention to me and taking me seriously as a scientist, as I said.
All right, so now we're going to talk more about science.
Woo! Science.
So we'll talk about what kind of science you work on. So let me start by asking you, when you meet a new grad student or a fellow scientist and they ask what you work on, what do you tell them?
So I work in transient radio astronomy. Transient meaning things that change over time instead of being constant, because most things, of course, in their universe do not change on our lifetime scale, like a galaxy or things like that.
So transient radio astronomy, so things that change in time.
Yes.
So,
for example,
yes.
If you're going for the 2-minute elevator pitch instead of the one,
I'm going for the really long elevator pitch.
Okay,
the elevator's stuck.
So, for example, if there's an exploding star or a black hole that shreds a star, or even if a exoplanet has a magnetic field and that flares up, or things like that, those are examples of transient signals that I study.
Anything that's sort of time dependent that we can observe in human time scales.
Yes.
And you said radio astronomy.
Mm-hmm.
So how is radio astronomy different from other astronomy?
Yeah, so, if your listeners recall the electromagnetic spectrum from high school science, most of the stuff astronomers do is in optical, so where our eyes are. But if you go lower frequencies down, you get to radio frequencies, which are, for what I do, the gigahertz part of the spectrum. That's where I study signals. And the reason we do that is different physical processes in our universe give off emission at different parts of the spectrum.
Okay.
Yeah.
So what are the types of stuff you tend to see more in the radio?
So primarily what we're looking at is, for my science, is called synchrotron emissions. So this is when electrons are spiraling in magnetic fields. So these are usually when you have a powerful blast wave going outward, you'll have these magnetic fields that are created from that pressure, and then these electrons spiral. That's what we see.
Okay, so you're seeing electrons spiral in magnetic fields, but generally that's often a signature that you have a shock wave.
Yes.
So there's a connection.
Or an outflow or something like that.
Or something like that.
Yes.
Where there's stuff colliding with other stuff. Or okay.
Yeah. And for the very explosive giant space explosions. Okay. That's usually what we're looking for.
And so some listeners may be wondering why that means electrons will be spiraling in electromagnetic fields.
Because there's a lot of stuff going on. It's a very turbulent environment, that is going to create your synchrotron emission.
Right. Okay. So that's generally the stuff that you work on, and you do this observationally. So you're a radio observer. So what does your research look like day to day?
Yeah, sure. So, as I said, we do have to set up, for example, observations for various telescopes. We use the VLA in New Mexico, Meerkat in South Africa, several other telescopes around the world. So it kind of depends on the stage of a project, I think is the way to put it. So, putting in the observations, the data reduction, stuff like that. And then we have several objects that we're studying, these black holes that are shedding stars, that evolve over years. So it kind of depends how far we are with the given project. In the data analysis and everything like that. And one or two I'm writing up now. Some we're going to keep monitoring for a while, see how they evolve.
So and I'm sure we'll talk more about black holes shredding up stars. But I hope so. When we had Brenna Moakler on, and so she talked a little bit about it from the theory side. But yeah, when that happens, so I guess, are you always on alert when somebody says there was a tidal disruption event?
So I'm part of a group where we keep an eye out for, there's all these various places where people report if there's a new tidal disruption event, is what these are called, TDE. And basically what you're doing in that case is, we see an optical alert, then we'll go follow up in radio. We are somewhat limited in distance because the luminosity in radio is not as good as in optical. So we're usually just going for the closer ones. Well, redshift of 0.1 is our cutoff, to be very technical about it. So, that's still 500 million light years or something like that. We're astronomically close is what we're talking about here. So we'll do that. We'll see if there's any radio emission that starts after this TD, which would tell you that something, basically, there's an accretion disk that forms when the star has gotten shredded. And then if there's an outflow from that accretion disk is what you'd see.
And so it sounds like you suggested sometimes you'll get an alert that says there's a tidal disruption event over here, and you look and then you just don't see anything in the radio? Yeah,
so the way it works is the statistics in the early times are not quite clear, but I think it's 20-30% of the time you'll see something within the first few months.
Okay.
And then the interesting thing there is, traditionally then we went off and did other things with our precious telescope time, because there's a lot of astronomical transients like gamma ray bursts, where if you don't see anything after the first 2 months, you're never going to see anything. And I think that kind of colored a lot of people's perceptions about TDEs.
Right.
But probably my biggest scientific claim to fame is that I was involved. There were 1 or 2 TDEs that people found were radio bright years later.
Right.
So it's we did a big survey and found that about 40% of all TDEs, if you don't see emission at earlier times, will be on in radio years later.
Okay. So that's kind of crazy because until normally these tidal disruption events, as Brendan was telling us before, they get bright and then they sort of fall off.
Yep.
And we
in the optical,
right? So so we kind of can model that and say like, okay, well, it should decay with time.
Yes.
But so you're right that we're also biased by other transients that do that, and there's no point in following up later. Although we might see something. Who knows? You have to have the motivation, right?
Yeah.
So then, first of all, we had no reason to look, but why did we? You were just curious?
As I said, somebody there was a first TDE called Assassin 15OI, and Assassin 15OI. It turns out if the VLA has a sky survey that it's been doing in recent years, like every 18 months roughly, it looks at the entire sky. It turns out after it had an initial peak, it was like a couple hundred days, like within a year after the TDE happened. But then it became much brighter in one of the more recent VLA sky surveys.
I see. So it was happening to look in that direction anyways at the same event, at the same location.
And so this came out and it was considerable interest in the community. And meanwhile, one of my collaborators actually found that if you go into the VLA sky survey and just look at all the TDEs, several of them are bright. So we actually this was a very lucky pandemic sort of situation for us, it turns out. The VLA has configurations. It goes, basically it has 3 railroad tracks that you move the antennas around on from the size of like a couple hundred meters to the size of Washington, D.C.
Oh, okay. So, I see. So they're on these railroad tracks so you can
move the telescopes to the kind of science needs different types of bigger, smaller. Smaller gives you more sensitivity, bigger gives you better angular resolution on the sky. Anyway, those are very set, but due to COVID, at some point it was stuck in a weird mid-configuration change for a couple weeks and they couldn't shift it because, quarantine, blah, blah, blah. And then they were like, well, if you could do science in this weird configuration, like submit a little proposal and we'll probably just give you the time. So we're like, hey, can we take a look at all these TDEs? And we did, and we found several of them had turned on. Wow. And that was actually the start of this project.
Okay, so then it's funny. So then all these models say they should decay with time in this sort of reasonable way, but then they get brighter again. Do we understand why?
Depends who you ask, but you're the theorist. So of course all the theorists are like, well, obviously
we all knew this all along.
Yes, this is trivial. I've actually had people tell me this is trivial. It's like, what's the answer then? But most of them just give me a very strange look, which is always fun with theorists. So it kind of depends.
Yeah.
The first thing to say is that probably it's not the same answer for all of them. I'd be very surprised. And so there's a few things here. So the first is there are some TDEs that will see the initial radio brightness, as I said, fairly promptly after the TDE happens. Then we see a re-brightening.
Okay.
It does look, there's been some recent work by Adele Goodwin et al. That shows that there's a second outflow happening at later times.
I see.
However, for a lot of these TDEs, we actually have good sampling and we see that there's absolutely nothing until hundreds of days or two-ish years or something like that later that you'll finally see this initial outflow. That's not entirely obvious.
Right.
There's 1 or 2 candidates that are potentially off-axis jets is what they're called. So in about, we always say 1% of cases for TDEs, I'm not sure you went into this with Brenna, 99% of TDEs are what we call non-relativistic outflows. So non-relativistic just means you don't have to take relativity into account. If something's going at 10% the speed of light, like a supernova shockwave, you don't have to care about relativity. 1% of cases, though, you have a relativistic jet that gets launched, and then you do have to care about relativity, and you probably know more about this than me. And we have 3 or 4, I guess, in the record of these jets that were pointed directly at Earth when they happened from TDEs, and that's how we know about them. But then you should say, okay, well, there's all these other ones that are not pointed at us.
If there are 3 or 4 that are pointed at us, then there should be way more that are not
pointed at us. And then the question is, okay, eventually, as the jet slows down, that will enter our line of sight on Earth as the jet gets bigger. So where are these off-axis jets?
Okay.
I can convincingly tell you that most of these TDEs are not off-axis jets
really?
because we can measure the physical parameters from the radio information.
I see.
And they're consistent with this non-relativistic population.
I see.
So
okay.
Yeah.
So all right. So there's so much information there.
I know. Sorry.
No, that's good. It gives us lots of stuff to talk about.
Yep.
So okay. So because it's good. When you know so much about things, there's like a lot.
As I said, this is the most interesting problem in astrophysics right now. So
exactly. So because you mentioned multiple things that tidal disruption events (TDEs) can do.
Yeah.
And these are once again just to clarify, that's when a black hole eats up a star.
Yeah.
And so one thing that might do is it could be have an outflow moving close to the speed of light that's beamed in some direction
in a tiny fraction,
in some fraction of them, and then it could, and then I guess most of them are not. And so then the other things that they could do is apparently have a second outflow.
Yeah.
And then if they are beamed, they could either be pointing at us or they could not be pointing at us.
Yeah.
And so, so there's a lot of different pieces.
Yes.
I want to first ask about why would there be a second outflow? The star got eaten up by a black hole, shreds it up. This material falls back onto the black hole and it eats it. So that's
why
one
is there
outflow.
Something years later?
Why years later?
I mean, I don't think there's been a very good explanation for this.
Okay.
And I should emphasize, of course, as I said, like a lot of these TDEs don't even they just have an outflow years later.
Right.
From the accretion disk. And that's a very strange delta time is the scientific way of putting that. Because you don't expect explosions to years after the fact when you don't see anything to be significantly different.
Right. So the outflow, gets bright and nicely goes down. It's not like it's constantly flaring or something like that.
I mean, there's definitely been some theories out there, like maybe there's something weird about the density environment, for example, around these TDEs. Maybe there's like a delayed breakout of some sort of jet, like if there's a cocoon around the TDE.
It's a long delay.
Delayed formation of the accretion disk has also been suggested. Like maybe the optical light is not actually the prompt formation of the accretion disk, and maybe what we're seeing later is the formation of the accretion disk.
Oh, so that there's something else that you're seeing the first time?
Yeah. The problem is TDE theory, as Brenna probably told you, gets computationally very expensive after the TDE has happened. So the models really don't go out that far.
Yeah.
It's like maybe 3 weeks max, and then they usually shut them off. So there's a lot of open questions at this later time scale that we don't understand.
Okay, that's but setting that aside, so that's one idea. But even if that idea isn't what's happening, then we do know that we can get multiple types of things by either having it be relativistic or not, or having it pointed at us or not. So it's kind of amazing how much physics is going into this. You got a black hole, it eats up a star, it shreds up a star actually, and then that gets turned into a disk, and then it accretes, and then it makes a jet somehow.
Yes, not in all cases.
Not in all cases.
I think it's pretty,
Some cases we don't get a jet.
But yeah, it is pretty fun. I mean, my kind of job pitch when I was trying to get my job in a physics department is like, listen, this is physics that we can't test in a laboratory on Earth. And this is a weird timescale. Like, it's a whole new parameter space for physics that we don't understand what is going on. And that's what makes it very exciting.
I guess maybe I'll stick to, because there's just so much to talk about there.
Sure.
If it's moving, you mentioned if it's moving close to the speed of light, then that would make a huge difference. So what are the things that I know the answer to this question, but what are the things that changes when it moves close? Because I'm sure our listeners would love to hear about things that have moved close to the speed of light. So what does that change about it?
Well, so when things move close to the speed of light, I mean, there's things like time dilation effects. We don't really worry about those in our observations. Usually what it translates to in our observations has to do with, for example, like the brightness of what it's doing, because it's just that much more energetic.
Right.
These become some of the most energetic things we can study in our universe. Like gamma ray bursts are the most energetic things, and TDE jets can be on par with gamma ray burst jets.
Right.
For example.
So it just gets so if it's pointed at us.
Yes. If it's pointed at us,
then it's super bright.
Yes.
But if it's not pointed at us,
that's the big question. So our best candidate right now is called AT 2018 HYZ, or Jetty McJetface, or Jetty is the nickname.
Really?
Yeah. Well,
was that your idea?
No, actually, it was my husband. So there was this object, as I said, AT2018HYZ, and it was the first TDE like this that I found that had re-brightened. And it brightened very quickly, like within a 9-month period, no detection, and then suddenly 1.3 millijansky, which is like pretty bright in radio speak. And it's been rising as fast as t to the 5th in its light curve for a lot of the periods since, which is like absolutely insane rise, exponential rise. Sharp. And yeah, so I went home, and this does not really like roll off the tongue. And my husband, who's not an astronomer, is like, true love is like, you get to name this, like, what do you want to call it? And he thinks, and he says Jetty McJetface. So I was like, okay, I guess we can roll with that. So it's called Jetty, but we weren't allowed to say that in our initial press release because that was just deemed undignified by certain people at Harvard.
I see.
Anyway, so the long and short is we said at the time when this happened, because there's a gap of like 2.5 years or something before the first detection from when the TDE happened. So we were like, we think it's a delayed outflow. The modeling fit that very well. So delayed outflow like a couple hundred days, 700 days later, and it was launched at mildly relativistic speeds. Because the theorists at the time said these off-axis jets should be seen much earlier, so we could rule that out.
Oh, really?
But then, of course, the theorists come back and they're like, well, actually, you know, this actually fits perfectly this off-axis jet model that I've now tweaked for,
Absolutely. So, well, I mean, that's the thing. I could have told you that was going to happen because when we do jet model, I have my grad student right now who's doing a bunch of off-axis jet modeling, and you can completely change where that, like the time scales and stuff by just changing your parameters.
Yeah, you guys are going to love my seminar later today. Then that's all I'm going to say.
Good. Yeah. But that's very interesting. So the idea then, I think we got hung up on the idea that it was Jetty McJetface and not about what it was. So it was something that we saw later in the radio, and the interpretation, or at least it sounds like there's two possible interpretations. One is that there's some delayed outflow, so it didn't have an outflow right away, but it waited some few hundreds
sometime, like
of
many
days.
of these TDEs, to be fair, do appear to do. Because most TDEs, we see them and then they start fading. Jetty is interesting because it's still rising. I said it was 1.3 millijanskys when we found it.
Now?
It's now about 35 millijansky at its peak frequency, peak emission. And so as I said, there are these models now. There's a couple ways we can test it. The main one is like, people are like, how much longer is it going to rise? It's like, well, you actually just have to keep checking in every few months. There's no way otherwise to know. The off-axis jet models that I've seen suggest we have about another 1,000 days. So in 3 years, if it peaks, then that will be consistent with an off-axis jet. But like highly off-axis, like almost 90 degrees. Right. The other one that we're actually trying to do is called very long baseline interferometry, which is when you link radio telescopes from like Hawaii all the way across the United States, including Germany. So basically a network that's almost the size of the Earth. Try to take a radio picture of this thing. And then if you can resolve it, because you have such a high angular scale, you could maybe say what is going on. Oh, because if it is off-axis, then you'd actually be able to see.
Then you might be able to see its actual motion through the sky?
Yes, and also measure its size.
And measure its size.
Yes, so we're still working on this.
Oh, that's very cool. Well, there should be a prediction if it's for those modelers should have a prediction for how it should move through the sky. Then.
Indeed.
Okay, very cool.
Yeah.
All right.
It's a very exciting object. That's for sure.
That is exciting. So I had the whole question asking you what was your what are you excited about right now? And
that's the answer for sure.
All right then. So maybe what we should do is I should ask this. I should shift gears and just ask this question, which is, in your opinion, why should we care about astrophysics?
So I have a 3-pronged answer for this.
Oh, good.
And the reason is, first of all, we should care about astronomy because we are humans, we are curious, we like to know the answers to things, yada, 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 the philosophical thing. I think a lot of your listeners, if they've reached this far in the podcast, probably agree with number 1. Number 2, though, is that we actually, do a lot of technology stuff, comes out of what we do and theoretical things. So the famous example is Einstein's relativity was the most arcane thing 100 years ago when it came out, general relativity. GPS systems would fail within 20 minutes if we did not have general relativity.
Right.
It turns out, given enough time, it'll become applicable. In radio astronomy, what we gave the world is actually Wi-Fi. It turns out the reason your Wi-Fi signals don't interfere with each other is a problem solved in radio astronomy. That patent, basically, what we gave the world is you guys all save far more money than anything that has ever been spent on radio astronomy in history. So we've secured it. And the third is actually our students, because we train the next generation with a lot of skills. Most of our students don't become astronomers. They end up doing other interesting things. But you get, a lot of really great skills. And also, it's much harder to measure, but how many people do you know when they were 6 years old wanted to be an astronomer when they grew up and are now an engineer or chemist or something else really exciting?
Right. So. Okay.
Yeah.
Well, it's funny. You obviously had an answer ready to go for that, which suggests you've been asked that a lot.
Oh, yeah. So. I do a lot of outreach. Yeah.
And so
this comes up.
And so for me, mostly I would get asked by family or something like that. What do you do with that?
Well, my experience is the reason you also give the 3-pronged answer is, as I said, like one answer might not suit. Like somebody won't believe in one of them, but they'll probably agree with one of the 3.
Probably agree with one of them, and it's
or at
funny,
least be polite and stop talking to you.
Okay, so that's your 3-pronged answer that you give to people. But for you, what is your answer? Like,
the reason,
why is it that you personally think is the most important reason that we should study astrophysics?
I mean, the reason I study astrophysics is because I love stories, and the story of the universe is the greatest and grandest one that we have. And I just like to be able to tell a small part of it.
Excellent. Okay. So then I guess I should ask, what do you think is the next big thing? What are you hoping for the next few years in astrophysics?
Well, this is a very strange time in astrophysics and science in general. So
this is meant to be an optimistic question.
I know, I'm sorry, but as a first-year faculty member, this is a very stressful time.
Right.
Because I'm like, well, the NGVLA is going to be great if we fund it.
Right.
It's like stuff like that. I think there's definitely, though, a lot of radio survey stuff that's going to come online. And right now, there's that, and the Rubin telescope or Rubin Observatory, which is going to come online the next year-ish.
Yes.
Is really going to revolutionize transient astronomy and TDEs and finding new ones.
So what in particular is going to be powerful about that?
The Rubin Observatory is down in Chile. It's an 8-meter telescope, and they're basically going to image the entire night sky every night, roughly, and just look for transients. And the data stream will be there. It'll be public. Anybody in the world can go and look for transients.
Okay.
And a lot of them are practical, like we're going to effectively map all the asteroids we can ever map.
Right.
And there's people in cosmology who want to learn about type 1a supernovae, seeing all those. But then there's also going to be thousands of TDEs in that data. So, the question of why are they turning on at late times? Where are all the jetted ones? Things like that.
Right.
We're finally going to have a sample. Like right now we're looking at maybe one every other month there's a new TDE.
Right.
And, you can imagine there's going to be over 100 that we could follow up on in radio is the current estimate. So that's going to be really exciting.
So just having the large numbers, right? At the moment, we look at each individual one and we say,
and it's
tell a
tough
story.
To build up that statistical sample.
Right.
Yeah.
And so each individual one will tell some story, and it was kind of this is what I think happened in this case.
Yes.
But yeah, once you have a big statistical sample, you can say, okay, here are the ones where they happen to be pointed at us. Here are the ones where they happen to be pointed, or you hope at least. Be able to separate out those concepts and be able to build a full statistical sample.
Yeah.
Okay.
So
great. Well, we look forward to it. Okay, I guess we can wrap up then.
Sure thing.
Thank you so much, Dr. Cendes, for joining me. I had a lot of fun talking science with you, and I hope you'll join me again sometime.
Yeah, sure. And if I can do a quick pitch.
Yes.
If people want to learn more about TDEs, I wrote an article in Astronomy magazine a couple years ago, which is titled, How Do Black Holes Shred Stars? Which if you just search on Google, it'll come up and it's free. And sometime in the next year, I'll have an article about TDEs in Scientific American. So keep an eye out for that.
Definitely. Check it out. Thank you very much.
Sure thing.
Incredible. There were multiple times there I got so interested, I almost forgot I was doing a podcast and wanted to start asking super technical questions. We ended up chatting a lot more offline about her data, and as a theorist, my brain is inventing all kinds of crazy new ideas about what could be happening. So thank you so much, Dr. Cendes, for telling us about Jetty McJetface. And thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. If you want to connect more or have astrophysics questions, feel free to follow us on Blue Sky at paulduffel.bsky.social. The music on the Astrophysics Podcast was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. Check out her work if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, professor of physics and astronomy at Purdue University.